Today's lecture will cover canonical transformations and differential equations. The main theme will be to put some flesh and bones on things that we learned on a very abstract level in mathematics. We learn lots of abstract stuff in mathematics unless we apply it to physics, or at least applied math, they'll be up in the air. If we take this real axis, an infinite line in both directions, arbitrarily set up an origin and arbitrarily assign an increasing direction, then at a point here, P may be labeled by its distance from the origin. So if this distance is x, I may call this point x. Now, we learned all that linear vector spaces in mathematics, and it's about time we employ that linear vector spaces with modern Dirac notation into this very simple real axis and points on a real axis. See, in the linear vector space analysis that I'll be using, I'll be dealing with entities like these. These are called kets. Then there is a dual space. And these will be called the bras. And I will assign an abstract operator for position. So, position operator. Denoted with a double bar like this, so we understand that it's an operator. And it's eigenvalue equation. So, operator hits a ket and gives me the eigenvalue times the same ket. Now, x's are real. This doesn't guarantee that x is a self-adjoint operator, but it can be made self-adjoint. So I'll say x is self-adjoint, as mathematicians call it, or Hermitian as physicists call it. This tells us that the eigenkets form a complete orthonormal set. What do I mean by this? First of all, the normalization x and x prime scalar product. When we start learning about these things, we should sort of imagine that these kets are column vectors and the bras are row vectors. So a row vector times a column vector is just a number. So this is a scalar product. And this scalar product is the Dirac delta function of the difference between these two values. That's orthonormal. The completeness is minus infinity to infinity dx x cat x bra equals identity. That's our starting point for the coordinate system. Then we start thinking about it and look for possible symmetry operations. Well, in this very simple-minded real one-dimensional problem, we have only one symmetry operation. That's, for example, shifting the origin to O prime. If this is a distance A, then the person who uses the white O as the origin will see this as x. The point P will be x. But for the orange observer at O prime, we'll see this point P at x plus A. So this symmetry operation, we can say there is a displacement operator A. When it hits x, it gives me x plus A. Now, d of A, I will not go into the details. The set with all the possible A values is a Lie group of one parameter, namely A. And it will have one generator, but we'll come back to that later. It forms a nice group. It is so important, it has a name. It is Euclidean in one dimension. So E1. Now, first of all, we should realize that d of A preserves norm. What do I mean by this? Xx is Dirac delta function at 0, and x plus A is also delta function evaluated at 0, because this 0 is x minus x, this 0 is x plus A minus x plus A. So it preserves norm. Things that preserve norm we call unitary. And unitary operators can be written in exponential form very conveniently as dA equals e to the imaginary unit, an operator A. For historical reasons, we have a minus here. Now, you realize that K is also self-adjoint or Hermitian. Meaning K prime is delta of K minus K prime, or integral minus infinity to infinity dk Kk is identity. This is orthonormality. This is completeness. This is what I would call a global approach, because A is a finite quantity. Now let's talk about local displacements, A being an infinitesimal quantity. Let us not forget that e to the minus I ka, when it hits x, it gives us x plus a. Now I'm slowly changing this a to a very small quantity. E to the minus I k dx hits x and gives me x plus dx. But what is dx? Dx is an infinitesimal. Dx is dx, but any higher power is 0. So I can expand this exponential and say this is identity minus ik dx hits x and gives me x plus dx. Now let's see what happens. This identity hits x. It is x. I can subtract it from here. So I have minus ik hitting x is x plus dx ket minus x ket divided by dx. This, of course, is the derivative, d dx of x. So I have this very nice relationship which ties the derivative operation to the k operator, which is called generator of translations. We are dangerously close to quantum mechanics because k, generator of translations, when multiplied by Planck's constant, becomes momentum. This is a very nice equation, but not all that useful because we do not work with x kets. X are usually bra, the dual space elements. So I would like to assign this as a homework problem. It is not all that difficult. It is the same thing. We just invert this to x e to the I ka giving x plus a bra. So for the homework problem, I would like that we show I x k equals to, you see, minus I becomes I and ket becomes bra. D dx of x bra. So d dx is I k, d square dx square is minus k square and higher powers. Now it's about time we should talk about differential equations. The most general second order linear differential equation would be f2 of x y double prime plus f1 of x y prime plus f0 of x y equals to 0. Now this is what we observe on a position screen, if you like to. The more abstract thing would be perhaps f2 of x operator, then the second derivative. the second derivative is minus k square. I don't say anything about y. Then f1 of x operator, then the first derivative, which is I k. Finally, f0 of x, together they hit y and give me 0. This 0 is 0 ket, but its scalar product with anything will give me 0. So this is the abstract version. This is the concrete version. Now it's about time we should start talking about canonical transformations. And conjugate variables. We saw a little while ago that x, when multiplied by e to the ik dx, gives me x plus dx. On the other hand, e to the minus ik dx, x is x plus dx ket. So kets and bras have a sign difference. Now let me start with the eigenvalue equation. X hitting its eigenket brings out the eigenvalue times the same eigenket. Now let me multiply this by e to the minus ik dx x. Here let me insert an identity in the form of e to the ik dx e to the minus ik dx x. So what have I done? I just multiplied this equation by e to the minus ik dx. This is nothing, this is 1. The other side, x is just a number, so the operator jumps over it, e to the minus ik dx on x. So what happens? There is this strange combination here. I don't know what it is. But this thing is x plus dx. I know it from here. This equals to x times, again, x plus dx ket. So I'm grouping these together. Now, what should I have here? You see, dx is basically 0. So it should, again, basically, this combination will be basically x. But that won't do, because when x hits this ket, it will bring out x plus dx as the eigenvalue. But this is only x. So it should be minus dx times identity. This triple product is simply x and the first order in dx contribution minus dx times identity. So the operator gives x plus dx, the second term subtracts the dx, and I end up with simply x. Therefore, I can now express this triple product, not in exponential form, but its expansion. I may say 1 minus ik dx x, then 1 plus ik dx. This thing equals to x minus dx times identity. Just this expansion equals to that thing. Now, here I'll have 4 terms. The x will be sandwiched between all sorts of combinations of these. Now, x sandwiched between the firsts, 1x1, that's x. Then x sandwiched between outside terms. This is 1, so this will be x I k dx. Then x will be sandwiched between inside terms, minus ik dx x. I don't write the identity. Then it will be sandwiched between last terms, but 2 dx's give me 0. So this is x minus dx times identity. Let's make the necessary cancellations. X, I can cancel the dx's. Then I can take this I to the other side as minus I. So I'll have xk minus k x equals I times identity. This is a very important relationship. Better notation would be using a commutator bracket, I identity. This is so-called while algebra. Actually, while algebra is 2 more redundant things. X with k commutator gives you I times identity. X with identity gives you 0. K with identity gives you 0. But this is while algebra. And this is the basis of quantum mechanics, the uncertainty principle, so on and so forth. The only thing you need is the Planck's constant to multiply k to make the generator of translations momentum. Now, it's about time we can talk about conjugate variables. So here, something like this tells us that x and k are conjugate variables. So 2 variables are conjugate when their commutator is I times identity. Then we say, let's complicate things a little bit and have functions of x and k. You see, in this algebra, there is x operator and then there is k operator. There is nothing else. It's one dimension. If it were larger dimensions, we would have more complicated things, but this is very simple, just x and k. So from the variables x, k, if I go to 2 functions, f of xk and g of xk, this is a canonical transformation. If further I have f g commutator equals I identity, then this canonical transformation gives me conjugate variables. So this implies f and g are conjugate. Now let me give an example. From xk, I go to x cos alpha plus k sine alpha, comma, minus x sine alpha plus k cos alpha. Now, what is the commutation relations of these? X cos alpha term will not see this because x and x commute. It will catch this. It will be xk cosine square alpha, the commutator, and this will be k commutator with minus x, which equals to commutator of x and k, sine square alpha. So they are conjugate. Let me go a bit further, a more special case. This is an example. A more special case would be where alpha is a simple minus 90 degrees, x, k goes into k minus x. So that's alpha equals to 90 degrees, special case. You may say, I have a strange coordinate system where I have x here, k here. Then I rotate it by 90 degrees. So x comes here, k comes here. So this is a very simple canonical transformation that gives me new conjugate variables. What are these? It's these, of course. Now it's time that we apply this to a concrete differential equation that we use all the time. Let's take the Legendre differential equation. Legendre differential equation is 1 minus x squared PL double prime minus 2x PL prime plus L plus 1 PL equals to 0. From the concrete differential equation to its more abstract form, parenthesis 1 minus x operator squared, then the second derivative, which is minus k squared, then minus 2x, then the first derivative, which is I times k, then L plus 1, close, PL is 0. At this point, I make the the canonical transformation, x goes to k, k goes to minus x. So, minus 1 minus k square, and k square is x square. The squares are not bothered by the canonical transformation. Just x square becomes k square becomes x square. Minus 2i, x becomes k, k becomes minus x. Plus L, L plus 1. PL. Shall I put PL? No, because this is a new differential equation. I should put another symbol. Let's say JL equals to 0. Now, this is not a differential equation that we would like to work with. Why? Because in a normal differential equation, I want the k square or k on the extreme right, so that it will hit this ket and it will differentiate it. So I must change the order of these things. Now, rewriting it a little bit more, minus 1 times x squared, this is minus x squared, then minus minus plus, plus k square x square plus 2i kx plus L, L plus 1, close, JL is 0. This is the ugly term. This is also ugly, but I'll find a solution, easier solution to that in a moment. Now, k square x square. I will use Weil algebra to get rid of it. K square x square is x square k square minus the commutator of x square k square. Because x square k square minus x square k square, they cancel. Then plus k square x square, which is this. Well, the first term, I keep it as it is. And this thing, using commutator properties, I take x to the left, x k square minus x k square x. Well, one more time, x square k square minus k comes here, x k xk commutator, then minus x xk commutator k. This k comes here, minus k xk commutator x. Finally, minus xk commutator kx. Well, this simplifies because xk in all these cases simply minus I. So this is x square k square minus this and that are both xk. This is just minus 2i xk, and here minus 2i kx. So I'll replace this k square x square by the new version of it. Minus x square, I do not forget, plus x square k square minus 2i xk minus 2i kx. I'm done. Now I start writing the rest of the operator, plus 2i kx plus L, L plus 1, close the square bracket, JL ket equals to nothing. You see, very conveniently, minus 2ikx and plus 2ikx cancel each other. So I have an entirely different differential equation. Rearranging things a little bit, I write x squared k squared first. Then minus 2ixk then minus x squared, then plus L plus 1 JL equals to 0. Now back to concrete form. Operator x squared becomes ordinary x squared. K squared is minus second derivative, so minus JL double prime. Then I come to minus 2i x. K is minus I times first derivative. Minus makes this plus, but I times I again makes this minus JL prime. Then I have minus x squared plus L plus 1. The whole thing multiplying JL equals to 0. Rearranging and getting rid of the minus signs, x squared JL double prime plus 2x JL prime plus x squared minus LL plus 1 JL equals to 0. This is the famous spherical Bessel differential equation. Now, one thing to think about is, and I don't know the answer to this myself, if in spherical coordinates you solve the wave equation, in spherical coordinates, the angular part contains PL. The radial part is JL. So in the same partial differential equation in 3 dimensions, I have these things that are the solutions of 2 differential equations that are related to each other by a canonical transformation. Now, to really test ourselves, if we have understood every little detail, a very comprehensive homework problem would be the canonical transformation of hypergeometric differential equation, which is x times 1 minus x, y double prime, plus square parenthesis gamma minus 1 plus alpha plus beta x y prime minus alpha beta y equals to 0. It is a formidable problem, but it has its rewards. Okay.